Hey everyone, and welcome to The Explainer. Today, we're diving into something absolutely fascinating, a new paper that tackles one of the biggest computational headaches in modern AI, the prefill bottleneck. Imagine a world where different AI models could just instantly share their memories, completely skipping the heavy lifting of reading a massive conversation from scratch. It's a literal game changer that promises to make AI serving drastically faster and cheaper. And the crazy part? The way they pull this off isn't through massive, expensive retraining. Nope, they use elegant, closed-form mathematics. It's incredibly smart. So let's just jump right in.
Okay, so here's our roadmap for today. We'll start by breaking down the LLM prefill bottleneck, look at this cool linear discovery, and then unpack the actual mapper pipeline. After that, we'll measure the performance, talk about when linear mapping actually isn't quite enough, and finally, look at what this means for a faster AI future. To get us started, I want you to imagine a sort of brain transplant for artificial intelligence. Think about it. Right now, if you're chatting with a smaller, highly efficient AI, and then the system decides your question is getting a bit too complex, it swaps in a larger, smarter model. Makes sense, right? But here's the catch. That larger model basically has amnesia. It has to reread your entire conversation history from token 1 just to catch up. So what if, instead, that smaller AI could just pass its short-term memory directly to the bigger one in an instant? That is exactly the problem we're solving today.
Section 1. The LLM prefill bottleneck and multi-model orchestration.
So you probably know that in production, AI providers aren't just relying on one giant, super expensive model for every single query. They use multi-model orchestration. They bounce between different sized models within the same family to balance cost and quality, like jumping from a 14 billion parameter model up to a 32 billion one mid-conversation. But every single time they make that swap, they hit a massive wall, the prefill bottleneck. Prefill is that first super expensive forward pass the AI has to do to read your prompt and build its key value, or KV cache. It's basically constructing its working memory. And the cost of doing this? It scales heavily with both the size of the model and the length of your prompt. Normally, the new model has to completely rebuild this cache from absolute scratch, which is just a massive waste of compute and time.
Now, this diagram brilliantly illustrates the solution to that exact problem. This is the high-level cross-model KV cache transfer pipeline, and let's thoroughly break down what's happening here. Over on the left, your prompt goes into a source model. Let's say it's a smaller 14 billion parameter QN3 model. It runs its standard prefill and generates a source KV cache. In a normal setup, the target model on the right, like the big 32B version, would have to process that prompt all over again. But check out the orange box right in the middle, the linear mapper. This thing takes the source KV cache and applies a per-head ridge regression to translate it directly into the exact format the target model is expecting. And here is the kicker. Notice that dotted gray line at the bottom labeled Target Prefill Eliminated? Yeah, because of this perfectly mapped KV cache, the target model can literally just jump straight to generating text. It bypasses the prefill phase entirely.
Section 2. A linear discovery. Let's talk about structural predictability.
Honestly, translating memories between two completely different neural networks sounds like it would require massive, expensive retraining. But these pairwise R-squared heat maps prove this stunning, hidden structural predictability. Let's look closely. On the y-axis, you have the source layers from a smaller model, and on the x-axis, the target layers in a larger model. The darker the red color, the higher the R-squared value, which basically means the variance is highly predictable using just simple linear regression. If you look down at the bottom row, showing the Qwen 314B mapping to the 32B model, do you see that incredibly sharp dark red diagonal line? That right there proves that a single source layer can powerfully predict its corresponding target layer. Also, take a look at the columns. The left column is the key cache with rope E included. That's the positional encoding data. The middle column is the key cache with rope completely stripped away. Notice how taking out that positional data makes the diagonal even sharper and darker? It's a much cleaner signal. And then the right column shows the value cache, which inherently doesn't have positional data, showing a slightly lighter but still highly distinct structural relationship. It's just beautiful math.
But it raises the question, how many source layers do we actually need to make this translation truly accurate? Let's analyze these concentration curves to find out. Here, the y-axis is our R-squared accuracy, and the x-axis is k, which just means the number of source layers we're selecting to do the translation. Look at how these curves behave. Way over on the far left, at k equals 1, the accuracy is, well, it's okay, but it's not great. However, as we move to the right, aggregating up to 4, 6, or 8 source layers, the curve shoots up super steeply before it finally plateaus. This is so cool because it illustrates that while one single source layer is a decent predictor, the really vital complementary information is actually spread out across multiple adjacent layers. So, to get the absolute best, most accurate translation, the target layer needs to draw its data from a handful of its most predictive source layers, not just one.
To put some hard numbers to those visual graphs we just looked at, consider this exact finding from the researchers. On Qwen 3 14b to 32b, one source layer explains 56% of variance in the target's keys and 32% in values, rising to 79% and 65% with multiple source layers. I mean, that proves with definitive mathematical data that aggregating multiple layers is the absolute key to unlocking the linear structure needed for a flawless memory transfer.
Section 3. The Mapper Pipeline Explained. Let's look at this closed-form solution.
Okay, so we know the mathematical relationship exists, but how does this actually get built into a functional system? We really need to slow down and unpack the specific mechanics behind this closed-form solution. This is the per-head linear mapper architecture, and it is dense, so let's walk through it step by step. Starting on the left, we have our source model layers. We use that R-squared data we were just talking about to select the top K source layers, basically the ones most predictive for our specific target layer. Now follow the blue and orange arrows. It is absolutely crucial to notice how the blue key data and the orange value data flow completely independently. The K and V paths do not share parameters at all. In the blue path, we concatenate all the keys from our selected K layers across all 8 attention heads. We then pass that massive chunk of data through a ridge regression. That's that blue box labeled WK plus BK. It calculates the weights and biases in a single closed-form mathematical solve. The resulting output is perfectly mapped to a specific head on a specific layer in the target model over on the right. Because they do this per head, it handles all those really complex dimensionality differences between small and large models without breaking a sweat.
If that diagram felt a bit overwhelming, don't worry, because we can synthesize the whole thing into 3 really simple, highly effective steps. Step 1, cross-layer source selection. You just select the top K most predictive source layers. Step 2, content space mapping. You literally strip the rope positional encoding right off the keys before mapping them, which means the fit is totally reusable across any context length. Step 3, fit an independent ridge regression. And you do this on a tiny calibration set of just 500 sequences. What's mind-blowing here is that because this is a gradient-free mathematical solve, it requires absolutely zero expensive backpropagation training. The whole thing only takes about an hour to compute on a single GPU node. That is incredibly efficient.
But we have to ask, do all 3 of those steps actually matter? Well, let's examine this ablation chart to find out. The tall gray bars on the right side of each little cluster represent our ground truth ceiling, basically perfection. The blue bars on the left are our full 3-step system, and as you can see, they get incredibly close to the ceiling. But now look at those green bars. That represents what happens if we remove step 1, the cross-layer source selection, and just try to use a single source layer, so K equals 1. On Arc, Challenge, and HeliSwag, the accuracy completely collapses. Similarly, look at the orange bars on MMLU and GSM 8K. That is what happens if we remove step 2, our inference ROPA handling. The accuracy literally plummets to near 0. So this definitively proves why every single piece of this 3-step pipeline is absolutely vital for the whole thing to work.
Section 4. Measuring the performance. Let's talk accuracy and latency.
Now that we actually understand how the engine under the hood works, let's look at the real-world performance metrics. Looking at accuracy retention across different transfer pairs on Arc Challenge, HeliSwag, and MMLU, see that dashed line across the top at 100%? That represents the target model running perfectly on its own, doing the whole prefill itself. Look at the blue and red bars representing our Tier 1 pairs like Qwen 13b to 32b and Llama 3.18b up to 70b. They are routinely hitting between 73% and 98% retention of standalone accuracy. That is honestly astonishing for a process that just completely skipped the entire reading phase. However, I also want you to notice the much shorter green bars on the right of each group. That represents the Mistral 8b to 14b model pair. Those models degrade really sharply. Keep that in the back of your mind, because we are going to explore exactly why that happens in just a minute.
By analyzing these benchmark curves, we can also understand exactly how that K-layer count impacts real-world accuracy. On the y-axis, we have transfer accuracy, and on the x-axis, we have the number of source layers used. Across HeliSwag, Arc, and MMLU, we see the exact same pattern. The curves climb sharply from K equals 1, and then they safely saturate and level off. But notice how it varies depending on the specific model pair you're using. The purple and blue lines for the QN models plateau very early, right around K equals 8. But then look at the red line in the middle graph. That's Llama 3.1 jumping all the way from an 8B model to a massive 70B model. Because the architectural gap between those models is so much larger, it actually needs to aggregate up to 20 source layers before its accuracy safely saturates.
Okay, so we've proven we can retain the accuracy. Now let's talk about speed, because this is where it gets fun. This table breaks down the latency of completely re-prefilling a prompt versus using our KV cache transfer on those Qwen 3 models. For a tiny 64-token prompt, the mapper is about 4 times faster. Pretty good. But look at what happens as the prompt gets longer. At a massive 32,000 token sequence, which is exactly the kind of context length you see in long, complex agentic AI workflows, the target model takes nearly 7,000 milliseconds to re-prefill. The mapper, it does it in 277 milliseconds. That is a jaw-dropping 25x latency speedup.
Plotting this latency on a log scale really reveals a clear picture of what's happening. The x-axis is the sequence length, from 64 tokens up to 32,000 on a log scale. The y-axis is latency in milliseconds, also on a log scale. Those dashed lines curving wildly up toward the top right, that represents standard target re-prefill. The computational cost scales exponentially with sequence length. Now look at the solid lines down at the bottom, representing our mapper application. Notice how they are completely flat at the beginning? That's because the mapper has a fixed dispatch cost. As sequences get much longer, it does eventually rise linearly, but it stays vastly faster than the exponential scaling of standard reprofilling. That massive physical gap between the solid and dashed lines on the far right of the chart, that's your 25 times speed up right there.
But what about an ongoing back-and-forth chat? Well, multi-turn handoffs remain incredibly stable. Here we are looking at the F1 accuracy score over 10 conversational turns. The dark blue solid line at the top is the 32 billion parameter model, handling the entire conversation completely on its own. The dashed light blue line right beneath it is our mapper, actively switching back and forth mid-conversation. What's so incredible here is that the dashed line stays remarkably steady over all 10 turns. The gap between them only widens by a tiny 1.7 percentage points. There is no cascading failure as the chat goes on. The math holds the context together perfectly, even while rapidly swapping brains back and forth.
Section 5. When linear isn't enough. Let's address those failure pairs. So earlier, we saw that the linear mapping degraded pretty heavily on Tier 2 models, specifically those Ministral 14B pairs. To investigate why this was happening, the researchers contrasted their simple linear ridge regression against a much more complex nonlinear MLP, or multi-layer perceptron. What they found was that the linear regression was experiencing these deeply negative calibration errors on the harder pairs. It just wasn't extrapolating the math correctly. But when they dropped in the nonlinear MLP as a replacement for the mapping phase, it successfully recovered the accuracy.
And honestly, this leads to probably the most profound discovery of the entire paper. The failure wasn't about the size of the error, but the placement of the error. It turns out the linear mapper was accidentally placing its mapping errors directly into attention-sensitive subspaces, which are basically the exact data channels the AI looks at most closely. So a tiny error got massively amplified. The nonlinear MLP brilliantly fixed this, but not by being perfectly error-free. Instead, it purposefully redistributed those residual errors away into attention-irrelevant directions. Basically, by simply hiding the math errors in places where the AI wasn't even looking, the MLP recovered a massive 37 percentage points on the HelloSwag benchmark for those failing models. Just incredible problem solving.
Section 6. A faster AI future and efficient model swapping. So, to wrap things up, we've just explored a training-free, mathematically closed-form breakthrough that can literally translate the complex working memory of one AI model directly into the architecture of another. By utilizing top-K cross-layer selection and stripping away positional encoding, it drastically cuts down energy consumption and tail latency for multimodal workflows. I want to leave you with this final, provocative thought to ponder today. If AI models never have to reread a conversation again, and context becomes perfectly fluid and instantly transferable across an entire fleet of varying intelligences, how much faster and smarter could your daily AI interactions become? We are literally entering an era of truly modular, shared AI memory. Thanks so much for diving into the math with me today on The Explainer, and keep exploring.